In this video, we're going to look at a slightly more complicated example of how we can apply Norton's theorem to simplify a circuit. Now, if you missed our first video on Norton's theorem, I suggest going back to watch that, where we cover the 3 steps needed to simplify a circuit using Norton's theorem. But in this video, we're going to look at a slightly more complicated example, and I've got a circuit here with 3 resistors, and I'm going to give these some values here. We'll say, first of all, that our supply voltage on the left-hand side is a supply voltage of 12 volts. That's cell on the left-hand side there. And then we can say that R1 is 220 ohms. We'll say that R2 is 330 ohms. And finally, R3 is 560 ohms. So we're going to apply the same steps as we did in our previous video, but we've got more resistors in this circuit than we did previously, and that's going to make things a little bit more complicated for us. But thinking back to step 1 that we talked about in our previous video, step 1 of Norton's theorem was to find the closed circuit current from terminal A to terminal B. And so what we have to do is imagine that we have closed our circuit here, and we now have a current flowing from terminal A to terminal B, and that's going to be our Norton current, IN. Before we can work out IN in this case, because we have different resistors that are connected in different arrangements, and IN is not quite as easy to work out as in our previous example. Before we can work out IN, we need to work out IS, which is the current coming from our supply there. So I'll mark that on there, IS. And what we'll find is that IS travels around the circuit, but it'll reach a junction here where some of IS will split, and some of it will go this way and some of it will go this way down through R2. And so before we can start thinking about how much current is going to flow through from terminal A to terminal B, I need to work out the supply current first. So starting at the supply, we know that there's a 12 volt supply, 12 volt cell there, and we know the formula for current is voltage divided by resistance. And so what I have to do is work out the total resistance of my circuit starting at the supply. So if we look starting here at the supply, we go around the circuit, we go through resistor 1 and we reach this junction here, as we said, and our current can flow this way or it can flow this way. And so because we've got that split at this junction here, we know that these 2 resistors, R2 and R3, must be in parallel. So we have, starting at the supply, we have R1 in series, then we split and we have R2 and R3 in parallel. And we can flow through R3 back to the supply or through R2 back to the supply. And so our total resistance here, I'll just mark it on as RT. We can say that RT we can express as R1 plus R2 in parallel with R3. Now, again, like I said in the previous video, this double slash is my shorthand for parallel resistors. If you're not sure how to work out resistors in parallel, then I suggest you go back to the video where we cover that topic. But here we know that R1 is 220 plus 330 in parallel with 560. Now, I've worked out 330 in parallel with 560, and I get an answer of 207.64. So my total resistance is 220 plus these 2 in parallel, which I know is 207.64 ohms. And that gives me a total resistance now of 427.64 ohms. So now that I know that, and I know that starting at the supply here is going to give me a total resistance of 427.6 ohms going from the supply and round through the circuit, I can work out my supply current, and I can say that I, or IS I should say, the supply current, is equal to V over R, Well, we know that the voltage is 12 in this instance, and the resistance we've calculated to be 427.64 ohms. So that gives me an answer of 0.02806 amps. Again, like I did in the last example, I'll multiply this by a factor of 1,000 to express it in milliamps. So that's 28.06 milliamps. So now we've calculated the current that emerges from our supply, and I can mark that on here as IS, and we said that IS is 28.06 milliamps. But what we find is that this current is not the answer to our Norton current, which is over here. The two currents are not going to be the same. And the reason being because IS, the supply current, flows from our supply. It's the current that flows through R1. But then we reach this junction here that we spoke about earlier. Some of that 28.06 milliamps is going to flow through R3 and become our Norton current. But some of that current is also going to flow this way through R2 and back to the supply. There's going to be a split in the current at this point here. And so what we have to do is use the current divider rule to figure out how much of this current, 28.06, actually ends up going through R3 and forming our Norton current here. So we're going to employ the current divider rule here. And if you're not sure about the current divider rule, we covered the current divider rule when we looked at Kirchhoff's current law. So I recommend going back to that video if you're not sure. But what we said about the current divider rule was, first of all, we can calculate the Norton current by splitting our supply current by using a fraction. So in this case, IN is going to be IS multiplied by a fraction. And what we said with the current divider rule was that if we want to work out in any split of two resistances, if we want to work out how much of our current goes through this resistor, then we need to put the opposite resistor on top. So in this case, we'll have R2 on the top of our fraction, R2 plus R3 on the bottom of our fraction. So let's put some numbers in to that equation there, because we know that IS is 28.06 milliamps. Now, I could express that as 28.06 times 10 to the minus 3 if I want to use SI units. But in this case, if I put my supply current as milliamps, then I'll simply get my answer in milliamps. So I'm not too bothered about that. Multiplied by this fraction, and we know that R2 goes on the top of our fraction, so that's 330 ohms on the top of our fraction there. And 330 plus 560 on the bottom of our fraction there. And if we calculate that, I get an answer of 10.40 milliamps. And that is our Norton current. So of the 28.06 milliamps that flow from the supply and through R1, only 10.4 milliamps flow through R3 and then become our Norton current. So we've used the current divider rule there to figure that out. So that was step one of Norton's theorem that we spoke about in our previous video. The next step, step two, is to calculate the open circuit impedance from terminal A to terminal B. So what do we mean by that? Well, first of all, by open circuit, we mean that we don't need this closed circuit connection anymore. So I'm going to take that out there. So we have an open circuit again, and we're asked to determine the open circuit impedance from terminal A through the circuit to terminal B. And again, we've got to be quite careful about where we start and where we finish here, because that's going to determine the arrangement of these resistors. So starting at terminal A, we see that we go through R3, the 560 ohm resistor. And then we reach this junction again. And we have a choice. We can go either this way through R1, or we can go this way through R2. Remember, when we're calculating closed circuit impedance, we can ignore any cells or voltage sources in the circuit. We can just short them out and pretend as though they were just a wire. So because we've got this split in the circuit, we can go either this way through R1 or this way through R2, round to B in each case. We know that R1 and R2 must be in parallel because there's two parallel paths we can take to B. So our expression for the total resistance, or the Norton resistance in this case, is going to be Rn, the Norton resistance, is equal to R3 plus R1 and R2 in parallel. So likewise, I've used that double slash notation for parallel resistors, but we'll put some values in there because we can say that R3 is 560 plus R1 in parallel with R2. Well, if I calculate R1 in parallel with R2, that's 220 in parallel with 330. I get an answer of 132 ohms. So that means that our total Norton resistance is going to be 560 plus 132, which is 692 ohms. Finally, step 3 asks us to draw our Norton equivalent circuit, our simplified circuit, and we've said that that circuit takes the form of a constant current source, which is these two overlapping circles here, in parallel with one resistor. So I'll mark that on here very quickly. So here's our equivalent circuit, and we can say first of all that our Norton current, that current source, we've worked out there as 10.4 milliamps, and our Norton resistance is 692 ohms. So once again, we have a Norton equivalent circuit here for the circuit above, and like I said in the previous video, what this means is that any measurement we care to take across these two terminals, A to B, in each instance is going to give me equivalent results. So I can measure the voltage, I could measure the current, I could measure the impedance. The two circuits should give the same results. They're completely equivalent to one another. The last thing I want to look at regarding this circuit is if we actually attached a load to this circuit, because our equivalent circuit here is still an open circuit. And what I want to consider is if we then attach a load to that circuit. So let's redraw our Norton equivalent circuit very quickly. We had that constant current source and we had our one impedance in parallel. So if I redraw that there, we said that we had a current of 10.40 milliamps and we had a resistance of 692 ohms. Now again, like we said, this is an open circuit, but I want to imagine that we've actually connected a load resistor to this circuit. So we've actually added another load, another resistor there, I'll call it RL, and that's completed this circuit now. So it's now a closed circuit. Now, by adding that resistor to the circuit, I've actually changed the parameters of that circuit and changed the operation of that circuit a little bit. But what I want to do is try and work out, just as we did in Thevenin's theorem, is to work out what's the power in this load resistor. So the PL, I'll mark it on as. We're going to try and calculate the power in that resistor. So to do that, we need to think about our circuit again, because we know that, first of all, we've got a current of 10.40 milliamps emerging from the constant current source there. But again, we get to a point now where we've got a junction in our circuit, and we'll find that some of that 10.40 amps will go this way, and some of that 10.40 amps will go this way. And so I need to work out the current in my load resistor before I can go on to think about the power in the load resistor. So we're going to have to apply the current divider rule again. So let's do that in this instance, because we can say that the load current, I'll call it IL, is equal to the supply current, 10.40, multiplied by a fraction. And what we said, just like before, is that if we want to work out the current in this particular resistor, the load resistor, then I have to put the opposite resistor on top, in this case the Norton resistor. So the 692 goes on the top of my fraction there, and let's say that this load resistor is a 500 ohm resistor, so I'll mark that on my diagram there, 500 ohms. So I have 692 plus 500 on the bottom of the fraction, and if I calculate that, I get an answer of 6.04 milliamps. Again, I'm happy to use milliamps here for the 10.40. I could express that as 10.4 times 10 to the minus 3, and I would get my answer as 6.04 times 10 to the minus 3. But I'm happy to know that if my initial current is in milliamps, then my answer will be in milliamps. So I'm not too bothered about that in this case. So finally, now that I know the current going through this resistor, RL, I can work out the power in that resistor, RL. And the reason I can do that is because we are familiar with the formula that we looked at in the previous video on Thevenin's theorem. We said that P equals I times V. Now, we also know from Ohm's law that V equals I times R. So where I have V in my circuit here, I know that V equals I times R, so I could easily say that P equals I times R, because V equals I times R. And so finally, my formula for power that I'm going to use in this example is I squared R. So let's go back to our calculation for power on the right hand side here. We can calculate the power in the load, PL, as I squared R, and we know that the current, I, is 6.04 milliamps. So I have to use SI units here, because milliamps is expressed as 10 to the minus 3. So that would be 6.04 times 10 to the minus 3 squared, multiplied by R, which I know for the load is a 500 ohm resistor. So P equals I squared R. And if I calculate that, I get an answer of 0.01824. It's a power, so I express that in watts. Now, better than expressing it as 0.01824 watts, again I'm going to multiply by a factor of 1,000, because I can say that that is the same as 18.24 milliwatts. So this has been a slightly more complicated example of using Norton's theorem, first of all, to simplify a circuit into its Norton equivalent circuit, which we see here in the top left. But then we've talked about adding a load to that circuit to complete the circuit, and we've determined the power in that load resistor.